Hi, I am Emerson Kumlat. In this video, I am going to present my Module 1 machine problem. I will be implementing my chosen numerical method technique on a programming platform. I have chosen topic set 3, which are Newton's method, Gauss Seidel, and Lagrange. I'll be using the C++ as my programming platform, which is the most popular programming languages available. C++ is a high-level, general-purpose programming language created by a Danish computer scientist Bjarne Stroustrup in 1985. The C++ can be accessed online using any web browser through this link. On this case, we don't need to install the C++ software on our laptop to run the application. Let's begin with the first topic, which is the Newton's method. Newton method is an open method that starts with one initial guess for finding real root of nonlinear equations. In this method, if x sub o is the initial guess, then the next approximate root is x sub 1, which is obtained by this formula. This is the algorithm of the program. First, we will require an initial guess from the user. That will be the x. Second, we will ask the user to specify the accuracy of the result. That will be the f's or the epsilon. The third step of the algorithm is the repetitive step that will be inside the loop. What is not done in the loop will calculate a new x, that is xn. The formula of xn is the initial value that is x minus f of x, that is the value of the function at that initial guess, and divided by the derivative of the function at that x. We will need to have this step to repeat a number of times until this x that we are finding, x of n, and the previous value of x is less than or equal to the accuracy that is desired by the user. Once we have found a value of x of n that is not greater than x by epsilon, then we will print that xn, which will be the root of the function. Here is the flowchart representation of the program based from the given algorithm. Let's have a polynomial function example that we will use on the program. Obtain a root from the given function using Newton's method. Terminate the process if the absolute error x is less than or equal to 0.0001. The function of x given is equal to x cubed minus 4x squared plus x minus 10. Let's proceed with the program simulation using C++. This is an online C++ compiler. I have here the source code. As you can see, we include some of the basic libraries including the CMath. I have already defined the function x cubed minus 4x squared plus x minus 10 and its first derivative 3x squared minus 8x plus 1. We define the derivative function because the C++ does not have a library that is capable of solving derivatives of any given function. The program is set to display 4 units decimal places. Let us run the program. The program will ask you first for the initial value of x. Let's say 4. Then it will ask you for the desired accuracy. Referring from the given example, the f's will be, or the epsilon will be 0.0001. When we hit enter, we will see a tabulated results of the x of o, the calculated value of x sub 1 using the iteration method, and the difference between the x sub o and the x sub 1. The program will display the calculated value of x sub o and x sub 1 repeatedly. Upon satisfying the terminating condition, it shall display a message at the bottom of the table, the root of the equation, which is 4.3069. Let's try to use the same program using a transcendental function example. Obtain a root from the given function using Newton's method. Terminate the process if the absolute error f's or epsilon is less than or equal to 0.0001. The function of x given is equal to 3x plus sine x minus e raised to the x. On the source code, I have already defined the function 3x plus sine x minus e raised to the x, and its first derivative 3 plus cos sine x minus e raised to x. The program is set to display 4 units decimal places. Let's run the program. The program will ask you first for the initial value of x, let's say 3. Then, it will ask you for the desired accuracy. Referring from the given example, the epsilon will be 0.0001. When we hit enter, we will see a tabulated results of the x sub 0, the calculated value of x sub 1 using the iteration method, and the difference between the x sub 0 and x sub 1. The program will display the calculated value of x sub 0 and x sub 1 repeatedly. Upon satisfying the terminating condition, it shall display a message at the bottom of the table, the root of the equation, which is 1.89. Thus, this program is effective in calculating the value of roots of both polynomial and transcendental functions. That's how the program for Newton method using C++. Let's move to our second topic, which is the Gauss-Seidel method. This is an iterative technique in solving systems of linear equation. It introduces a newly computed variable to the next computed variable rather than the next iteration in order to forcefully accelerate convergence, thereby improving set of computed variables for the next iteration. This is the graphical substitution process. The method follows 3 steps. Step 1. Rearrange the order of the equations in a manner that the dominant coefficient for each unknown variable lies in the main diagonal of the system of linear equations. Step 2. Obtain the iterative formula for each variable by transposing the dominant variable and dividing the equations by the dominant coefficient. Step 3. Begin the iteration by substituting the initial values to evaluate the first variable, then it is substituted onto the next iterative variable to obtain their new values. The process is repeated by substituting the variables on the next iteration until the terminating condition is satisfied. This is the algorithm of the program. First, we enter the number of equations n. This number will also determine the number of unknown variables. Second, create a size n matrix, which will be the augmented matrix. This matrix should follow the order stated from the step 1 of the Gauss-Seidel method. Create an array X of size n, which will store the solutions. Enter the elements of augmented matrix row-wise. Enter the initial values of the variables. Enter the specified terminating condition F's. Perform iteration to calculate x sub 1, x sub 2, and so on until x sub n. Create a loop that calculates x sub 1, x sub 2, and so on until x sub n. Compare the new value with the last value. If the value of all variables are different from their previous with error more than epsilon, then flag must be n and hence stop the loop. Print the contents of x, which are the calculated roots. Here is the flowchart representation of the program based from the given algorithm. Let's try and execute this example onto our program. Determine the mesh currents using Gauss-Seidel method. Terminate if the absolute error is lesser than or equal to 0.0001 for all variables. The given equations are 15 is equal to 2 I sub 2 minus 3 I sub 3 plus 5 I sub 2. Negative 21 is equal to negative 6 I sub 3 minus I sub 2 plus I sub 1. 22 is equal to 2 I sub 2 plus 7 I sub 1 minus 3 I sub 3. We have to rearrange the order of the equations in a manner that the dominant coefficient for each unknown variables lies in the main diagonal of the system of linear equations. We put the coefficients in augmented matrix form. Let's begin the simulation. The source code is loaded on the program interface. As you can see, we include some of the basic libraries. The codes that will ask the user to input the number of equations, enter the elements in augmented matrix, enter the initial variables and the accuracy of the terminating condition epsilon. The code limits its output integers into 4 decimal places. The codes for the loop containing the iteration formula is included and so on. Let's run the program. Click compile. The program will ask number of equations, which is 3 from the given example. Next, it will ask the elements of the augmented matrix in row-wise. Next, input these values according to the example given. 7, 2, negative 3, 22, 2, 5, negative 3, 15, 1, negative 1, negative 6, and negative 21. We are asked to enter the initial values of the variables 0, 0, 0. Enter the accuracy epsilon 0.0001. After entering, the condition was satisfied at 8 iterations with unknown variables. X sub 1 is equal to 3.5938, X sub 2 is equal to 3.6563, and X sub 3 is equal to 3.4896. This program can also solve for 2 equations with 2 unknown variables or 4 equations with 4 unknown variables and so on. That's how the program for Gauss Seidel using C++. Let's move to our third topic, which is the Lagrange interpolating polynomials. A curve-fitting technique that constructs a polynomial f of n of x of a degree n-1, where n is the number of data points given by this function that contains some Lagrange term and the function f of x of y, whereby the Li of x, or the Lagrange function, is the continuous product of x minus x sub j divided by xi minus xj. This is the algorithm of the program. First, we have to enter the number of values or data points. Then, we have to enter the value of x to find y. Enter value of independent variables, say x of 0 or x of 1, and so on, whose corresponding value of dependent, say f of 0, f of 1, and so on, is to be determined. Begin Lagrange interpolation. Print the output. Here's the flowchart representation of the program based on the given algorithm. Let's try and execute this example onto our program. Apply Lagrange interpolation to fit the given set of data points into a function and determine the force F at distance of x is equal to 12.5 feet. These are the given data points. Let's begin with the simulation. The source code is loaded on the program interface. As you can see, we include some of the basic libraries. Let's run the program. Click Compile. First, the program will ask the user to enter the number of data points. In our example, it's 6. Enter. Next, the program will ask the value of x to find y of x, that is 12.5 in the given example. Enter. Now, the program will ask for the x data points 5, 10, 15, 20, 25, and 30. Last, the program will ask for the y data points 9, 13, 14, 10.5, 12, and 13. Press enter and we get the corresponding value of y of x when x is equal to 12.5. The answer is 14.5312. The Lagrange values will also be printed on the program. That's how the program for Lagrange interpolating polynomials using C++. These are my references. I've got the scripts from braggitoff.com. Thank you.